No, I have my next one right now. I'm sorry, I didn't know you were talking. You guys give me 1 minute, I'll be right back. Oh, this class wasn't helpful. I'm sorry, I'm back now. First, are there any questions or concerns? No.
Hi, this is I had sent an earlier.
Okay, you're
wondering-
Kevin, you're cutting in and out. Can you say it
Okay,
again?
sorry. Can you hear me now?
Yep.
I had sent an email earlier today asking about the quiz. I had taken it and I'm pretty satisfied with my first score. But
Yeah.
if I take it again, will it just record the highest score?
Yes.
Okay. And also, when I look at my grades, it's not showing up that I did the chapter 1 practice, even though it is completed.
Can you send me a screenshot showing that you completed it?
Okay, I'll do that.
Yeah.
Okay, thank you.
No, I understand. Thank you. Anything else?
I also might have had the same issue with the chapter 1 practice. I'm not sure if it says I completed it, but I did. So if anything, I'll email you a picture as well.
Yeah. Send me a picture, bro. Yeah, send me a picture.
I have a question.
Go ahead.
Is it okay if I leave like 10 minutes early?
You can really leave whenever. Because I can't really see that that's fine.
Oh, what's it called? I'm paying attention, but like I have a meeting.
No,
with
I
another
understand.
at this
I
time.
understand. No, go ahead. That's fine.
Thanks so much.
You're
It's
welcome.
like the meeting is around like 1:30, so
Yeah,
it's still like an hour away.
I understand. What other issues?
The chapter 1 quiz.
You're on mute. I can't hear a thing you're saying. You were there and now you're gone. Nope. Give me, Claire, let me see if I can't unmute you from here.
Okay.
Now
Can you
you're
hear me?
there.
Okay. Is the chapter 1 quiz due tomorrow at midnight?
I thought it was due yesterday, but I'm not sure.
It says
I'm
September.
pretty sure it says Wednesday.
Okay, then yes, it's due tomorrow night.
Okay, perfect. Thank you. I was just, everyone was talking about it and I just thought, oh my God, did I miss a deadline? And
No,
I did
you know what? If you miss a deadline, let me know, tell me which one, I'll extend it out for you.
okay, thank you. I appreciate
You're
that.
welcome. Other issues? Other questions? Yeah, let me tell you right now, if you email me right before this class or email me within the 4 hours before this class, I have a class right before this and it's 3 hours long. So I probably will not see your email. And so feel free to bring it up with me here. And nothing is that life-threatening. We can figure out really anything. Okay. You see that my screen is bumping around because my cat is massaging his jaw against the corner of my monitor right now. He really does this to get attention. He didn't do it at all in my first class. Okay, bear with me. Yeah, you're right. Those chapter 1 stuff, it's due tomorrow night. So chapter 2, and I think we were on 25. So bear with Leo, you can't be right there. No, you can't be right there, bud. Sorry, disciplining my cat. Besides, he's going to move on to the keyboard. He really is a law unto himself. All right. Of course, it's not going to tell me which one we're on. Were we about right here? Okay, let's start right here. So I'm going to back up just a little bit more. So when atoms combine with other atoms, they're held together by chemical bonds. This is an energy relationship. What this represents. The likelihood that an atom will form a chemical bond depends on the number of electrons in its valence shell. An atom is most stable when its valence shell is full. Remember, this is the octet rule. The first shell likes 2 electrons. The valence shell is always the most outer shell of an atom. And it likes, in the outside of hydrogen and helium, it likes to have 8. Every other atom likes to have 8, except for hydrogen and helium, which have 2. But every shell likes to have 8. It will either, it can give up electrons to get an outer shell that only has 8, to develop an outer shell that only has 8, or it can add electrons to get a shell that only has 8. But the most stable is an atom that has 8 in its outer shell. Can give up, it can take on. We'll talk in a second about the fact that it can share, but it likes to have 8.
What do you mean that it can give up? Does sometimes
It can release electrons to another atom.
okay. So does it have more than 8 sometimes, or
Not in its outer shell.
okay?
One thing we'll talk about is no, actually, never mind. Yeah, not in its outer shell. Outer shell, it wants to have, it needs to have 8. So an electron, one other thing with regards to this, each electron shell within an atom represents a different energy level. If you think about this, we've all played with magnets. Magnets like to stay close to one another. You know, their opposite ends, they positive charge, negative charge, 2 ends. If you just let them go, and if I'm holding one here and I'm holding one here, bear with me. Let me see if I have one. Give me 1 second. I have 2 magnets here. One magnet, let me say, stop sharing for 1 second here. Okay, so 2 magnets here. One magnet, another magnet. This is my positively charged proton. This is my negatively charged electron. This is my nucleus because it contains the protons. This is my electrons that are orbiting around. Why do my electrons orbit my nucleus? What keeps them orbiting? Why do they even want to stay close to the nucleus? What's the charge on the proton? What's the charge on the electron?
Because it's neutral. Protons positive, electrons negative.
Yep. So it's actually the opposite charges. So the electron orbits the nucleus because of the negative charge and the positive charge attraction. Now, my question for you, Caitlin, is what prevents the electron here from colliding into the proton? If it's staying because of the orbiting, but what's preventing it from just moving closer and falling into the nucleus?
Because of the layers, because you can't have 2 or more electrons in the first layer and then 8 in the other layer?
Well, that would they're negatively charged, so it's gonna possibly still go in, right? Let me put it another way. If I right about right here, if I let them go, it falls into it, right?
Mhm.
I let it go, it falls into it. However, there's a certain, if I hold it like this and I hold it, they're still attracted to one another. But they're not coming together. So when I'm holding it, there's an energy level there that's holding it out, right? My hand is forcing it not to move into it. So there's a certain energy right there. If I want to pull this electron out further away, I can. If I add more energy, if I make my hand, push my hand, pull my hand out, I can add more energy and push this electron out even further. If I let go, actually that didn't work very well. If I let go, it falls back into it. If I give up the energy that was holding them apart, it falls into it. Or it will fall back into the next shell. So here's one shell, here's another shell. So closer to the nucleus, there is a force that's holding that electron out in the orbit. However, the further I get away from it, the weaker that energy, that energy was holding it here is now not so strong, right? Now, with that in mind, the further the electrons get away from the atom, the more likely the further the electrons get away from the nucleus, the more likely they are to react with other things. Because they can easily be given up at that point. There's not that pull to hold on to them as well. So each electron shell within an atom, represents an energy level. There's a certain energy that's involved in keeping this electron right here from falling into the nucleus right here. I can give this little electron a little bit more energy and pull it out even further away. This electron that I've now pulled out further away from the nucleus can give up its energy and move back in. Nevertheless, the further I pull it out, the less pull it's going to have to the nucleus. So the further I pull the electron out, the less pull it's going to have, or the less force there's going to be that attracts it to the nucleus. So inner electrons that are closer to the nucleus do not take part in reactions with other atoms because they're held more tightly by the atom's nucleus. Electrons that are farther from the nucleus in a valence shell have the highest energy ability to overcome their attraction to the nucleus and interact with other atoms. So valence shell electrons follow the octet rule that determines the number of bonds. And the ones in the valence shell are the ones most likely to interact because they're the ones that have the least amount of, are least attracted to the nucleus. Paisley, stop that. Don't do that. So with this in mind, atoms that have only, so bear with me. What is the charge on a proton?
Positive,
Positive. What's the charge on an electron?
Negative.
negative,
Negative.
Right. So the overall, so if the number of protons in an atom equals the number of electrons, what's the overall charge on that atom?
0.
0. Now, with that in mind, what if we have an atom like sodium here that has 11 electrons and 11 protons? It has a 0 charge when it has, there's an electron right here. So it has 2 in its first shell, 8 in its second, and then it has 1 more out here. It has a 0 charge, sodium at this point, because it has 11 protons and 11 electrons. It has a 0 charge. However, its most outer shell doesn't have 8 electrons. Right? So it's not stable for that reason. Is it easier for sodium to give up an electron, or do you think it's easier for it to take on 7?
To give up.
Give up one.
It's easier for it to give it up. It doesn't, the choice is either to give them up or take them on. But we want 8 in the outer shell. So an atom that loses electrons, like this one right here, sodium, loses electrons to have 8 in its outer shell. This atom now, remember, it had 11 protons and 11 protons and 11 electrons, and then it gave up one of its electrons. So now it has 11 protons and 11 protons and 10 electrons. What's its overall charge?
Positive,
Positive what? If it just gave up 1 electron, it's got a positive charge of 1. Because the number of protons exceeds the number of electrons by 1. Atoms that have a positive charge are called cations. On the other hand, so chlorine here has 17 electrons. Has 2 in its first shell, 8 in its second, and 7 in its last. Is it easier for it to take on 1 or give up 7?
Take 1.
It takes on 1, and it takes it, and because sodium wants to give up 1, it takes on the 1 from sodium. Now it has 17 protons and 18 electrons. What is its overall charge? If it has 17 protons and 18 electrons, what's its overall charge?
Negative.
It's a negative. And what is it? Is it a negative 1, 2, 3? What is it?
-1.
It's
-1.
-1. That's correct. And then because the sodium ion and the negative chlorine ion are of opposite charges, they're attracted to one another. That's the basis of an ionic bond. Sorry, that's the basis of an ionic bond. Any questions about this? So reactive properties are of a chemical or chemical behavior of an atom mostly depend on what?
I think D.
Is it D?
Why do you think it's D? Someone tell me why you think it's D.
Because when they're in the outer shell, they can go migrate with other atoms.
Right. What if that outer shell contains 8 electrons? Is it going to react with other things? No, it's not.
Guess no.
No, it's not. It's not, because if it's got 8, it doesn't need or want more. It's full. Even if it has a charge on it, it's full. When atoms gain electrons, what happens?
I think positively charged.
Think through it one more time, Toyin. What's
The
charge
atom
on
D.
become
electron?
positively charged.
What?
I said B.
But no, think through this one more time. When an atom gains an electrons, what are the charge on electrons, Toyin?
Negative.
So when an atom gains electrons, Toyin, what do they become more positively charged or more negatively charged?
Negatively charged.
Correct. Why would their atomic mass, why would C not be correct here? Why wouldn't
Because
that?
atomic mass is protons and neutrons.
Exactly. Their atomic mass is not affected by the number of electrons. Good job. So inorganic compounds or salts are ionic compounds containing cations that are other than hydrogen ions and anions other than hydroxide. And when they dissolve in water, the ions dissociate. into electrolytes that can conduct an electrical current in solution. Most salts found in the body are sodium chloride. The most common are sodium chloride, calcium carbonate, and potassium chloride. You will learn that I'm going to start the first time that I ever tell you, most of the time, the first time I show you how I will spell out what this means. But then I'm going to ask you from there on out to start Googling them. You can do this on your own. If you put in to Google, you say NaCl, it's going to tell you what that's the full name of that salt is. It's sodium chloride. I'm going to start doing that because I want you to get used to the chemical symbols. So calcium, CaCO3 is calcium carbonate. KCl is potassium chloride. Oh, one thing that we didn't, so when these ions, when they dissociate, what that means is that you can conduct a charge through the solution. Most often, this is electrolytes that are moving from one to the next.
Excuse me, what do you call CaCO?
What?
What do you call the CaCO3?
It's calcium carbonate.
Okay.
The most common ions are iron 2+, iron 3+, copper 2+, zinc plus, iodine plus, and magnesium 2+. When you think of iron, this Fe2+, what does that tell you about the number of protons and the number of electrons in that ion? That's an ion right there. How many electrons are there more than protons? Or how many protons are there over electrons?
2.
Yeah, there's 2 more than electrons.
There two more protons.
Oh yeah, that's what I meant.
I know. I was guessing that's what you meant. And same thing for the iron. There's 3 more protons than there is the number of electrons. Copper, there's 2 more protons than there is electrons. In the case of zinc here, I'm gonna reverse it. I'm gonna say there's 1 less electron than there is protons. Means the same thing. Iodine, the same thing. There's 1 more proton than there is an electron. Electrolytes are substances that ionize in water, so they separate in water, and they form solutions capable of conducting electrical currents. We can detect electrical activity of muscles, the heart, and the brain because electrolytes in the body fluids conduct electrical currents from these organs to the skin surface. This right here is an electrocardiogram. So electro and cardio meaning heart, gram meaning you're calculating the electrical activity. This is a lie detector test. This is an electroencephalogram, as my mother just told me a second ago. If you think cephaly is being head, encephaly is the brain. So this is an electroencephalogram. Ways that we look at the heart's electrical activity, we look at the brain's electrical activity. So the way oftentimes seizures can be detected. Electrolyte balance is one of the most important considerations in patient care. Imbalances lead to coma or cardiac arrest. Most common electrolytes are calcium chloride, disodium phosphate, magnesium chloride, potassium chloride, sodium bicarbonate, and sodium chloride. So in water, they dissociate into their cations and anions. Similarly, but this is kind of a similar to like a radioisotope that's going to give off beta rays, which are the electrons. But free radicals are highly reactive chemical particles, so molecules or atoms, with an odd number of electrons. So they have an unpaired electron in an orbit. These are normally produced all the time. They're produced in normal body reactions. Every time your cells undergo cellular respiration and they break up an oxygen molecule, they form a free radical. And so they take the oxygen molecule right here and form a superoxide anion, which is a free radical, potentially dangerous because they easily combine with other molecules to change the electron configuration. When you have an unpaired electron, you're going to try to pair it up with something else. And then you unpair, and then causing something else to become changed also. And if we keep changing the structure of atoms, we change their function, causing chaos. Just like structure and function in all other of our body structures, change the atomic structure, you change its function. So free radicals are bad because they easily combine with other things, converting them to free radicals that then go on to convert other things to free radicals and so forth.
And you said they easily combine with other like molecules because
any other biomolecule. So
Because
they
it's
easily
okay.
combine with, some more than some biomolecules more than others, but they easily combine with other biomolecules, converting those molecules into free radicals.
Is this how a virus would work, like HIV or something like that?
No,
No, okay.
that viruses work through injecting their DNA into a cell and hijacking the cell to make their what they want.
Okay.
Kind of like a hijackers we just went over September 11th, like a hijacker of a plane taking over a plane. And they take on they use the machinery of the cell to produce the virus molecules. So they infect it, they enter the cell, and then they overtake the cell to produce more viruses. And HIV is an especially nasty one because it infects cells of the immune system. And because our immune system is what actually protects us against viruses, when we're disabling the immune system because it's getting infected by a virus, the result is that you can't even fight it off. When next semester, when you go over the immune system, bring this same question up. Because
Okay.
because HIV for that reason is really, really nasty.
I have a question. So when it's okay, when they go to like destroy the other things, is there like, do they just kind of wither away, or do they keep destroying?
Well, they change their structure, they change their structure by binding to them. They add more electrons to them, which changes the structure of them. And if you change the structure of something, you change its function. And if it's no longer doing the function that you need it to, then what's the point?
Right.
So that's what it does. Can it and most often when it changes the function, it doesn't create, it's rarely ever going to create a new function. It's just going to disable it. Yeah, that's a really good question. But yeah, it's all related back to that structure and function idea. So these radicals lead to the destruction or the disabling. And for Caitlin, her idea, she was right, the disabling of other molecules in the body. Oxidative stress is a state that occurs when there is too many free radicals in the body cells. This can cause cells to lose their structure and function, leading to diseases like cancer, diabetes, aging, atherosclerosis, and at least 45 others. Antioxidants, like bear with me. Very, very touchy little mouse. Antioxidants like zinc and vitamin C and vitamin E and beta carotene inactivate free radicals. Now, how do they do this? Antioxidants reduce free radicals. And we'll talk about oxidation and reduction here in a little bit. But reduce, what that means is they give an electron to the free radical. So we know that free radicals are atoms with an odd number of electrons. So they have an electron that's alone in an orbit. The antioxidant donates an electron to the free radical, neutralizing the free radical. So the free radical receives an electron from the antioxidant, and a stable electron pair is formed, and the result is the free radical is then neutralized. The top antioxidants in the human diet, or our diets, are vitamin A, vitamin C, vitamin E, selenium, that's one of the trace metals, selenium, lycopene, and lutein, something like that. Another way that we can get rid of some free radicals, or at least in the case of superoxide, is through an enzyme that we have called superoxide dismutase. This is an enzyme that breaks down potentially harmful oxygen molecules in cells. So it specifically is breaking down superoxide. It's a very important antioxidant defense against oxidative stress. Because like I said before, during cellular respiration, where we need oxygen to breathe, every time we take in an oxygen molecule and we break it down because to use it for cellular respiration, the result is that we create a superoxide molecule, which is a free radical. Superoxide dismutase converts it to hydrogen peroxide. Hydrogen peroxide, through the use of peroxidase catalases, changes it to water, and water is not harmful. A bond, remember this is that ion bonding. So a bond formed by a transfer of one or more electrons from one atom to another that produces ions that are attracted to each other, creating a salt. And the example that we used before was sodium chloride. So sodium, to get its octet rule and get its valence shell so it only has 8, gives up an electron to chlorine. At that point, sodium has a positive charge on it, and chlorine has a negative charge. And then they're attracted to one another just based on their opposite charges. So ionic bonds are when one atom either completely takes another atom's electrons or completely gives up one of its atom electrons or more. And then they're held together based on their opposite charges. These bonds are commonly formed between atoms with 1 or 2 valence electrons and atoms with 6 or 7 valence electrons. Because of the likelihood of being able to fulfill the octet rule and have 8 in the valence shell. So an atom with only 1 or 2 valence electrons is more likely to give those up to an atom. And an atom with 6 or 7 valence electrons is more likely to take on 1 or 2.
So what if you have one that's like 50-50? Or is there ever that case?
Is there ever that? They tend to share them, I think.
So it's not like giving up, like say.
No, it's not so much, yeah, it's not giving up at that point. They tend to share them. And we'll see that here in a moment. Caitlin, you're just jumping ahead on me.
And I don't know. There's questions. I don't even look really at the
It's all
PowerPoints
right.
until
You're
class.
all right. I'm messing with you. It's all right. In the dry solid state, ionic compounds are salts, which do not exist as individual molecules, but they exist as crystals with large arrays of cations and anions. So the cation sodium, the anion of chloride. And they exist as large arrays of the cation sodium, anion chlorine. The most common and strongest chemical bond in the body are covalent bonds. These are the ones that Caitlin was talking about, where bonds are formed by electrons being shared by atoms. The electrons will occupy a single orbital. Wonder, with what Caitlin said, we're going to talk about carbon. We may talk about it today, or we'll talk about it on Thursday. But we're going to learn that it's one of those 50-50 ones, Caitlin. It has 4 in it. It has 4 in its valence shell. So examples of these covalent bonds are oxygen, right here, shares 4 electrons, 2 pairs. Each pair contains 2 electrons. So it has 2 pairs of electrons altogether sharing 4. Sharing 4 electrons and 2 pairs. Each of the pairs are represented by a bar. Methane gas shares this with carbon, shares 4 electrons, 1 with each hydrogen. Oxygen in water shares a pair of electrons with one hydrogen and then another hydrogen. A single covalent bond is where one pair of electrons are shared. So this is two electrons being shared between the two atoms. And because there's two per pair, we have one pair of electrons or two atom electrons being shared. So this is what makes a single covalent bond. A double covalent bonds occur when two pairs of electrons are being shared, like in the case of the oxygen gas molecule. 1, 2, 3, 4. And each bar represents two electrons. A triple covalent bonds occur when three pairs of electrons are being shared, like in the case of the nitrogen gas. In an oxygen molecule, how many electrons in total are being shared between the two oxygen atoms?
Is it 4?
Why do you think it's 4?
I lied. Maybe it's 2.
I think you were right the first time. Why do you think it's 4?
Is it because it has like 2 hydrogen?
Well, no, the oxygen molecule doesn't have any hydrogens. Because it shares two pairs, it has two pairs of electrons. It has two double bonds, or say it has two covalent bonds. And each one of those bonds contains two shared electrons.
What is the little 2 next to the L?
That's saying that there's two oxygen atoms.
Okay.
So nonpolar covalent bond. The shared electrons in the covalent bond are spend approximately equal time around each nucleus. And the electrons are thus shared equally between the bound atoms. The atoms that are sharing the electrons share those electrons equally. So the nonpolar covalent bond. When atoms don't share electrons equally, the result is polar covalent bonds. If you think about the opposite poles on the planet Earth, two very opposite ends. Polar covalent bonds form because the nucleus of one atom attracts the shared electrons in the covalent bond more strongly than the nucleus of another atom. So I think it might have been Caitlin asking me what that little 2 meant on that oxygen. It's what it means here too. It means that there's 2 hydrogens attached to 1 oxygen. In this case, there's 3 hydrogens, 1, 2, 3, attached to 1 carbon. So the nucleus of 1 atom in a polar covalent bond shares the electrons more strongly, attracts them more strongly than the nucleus of the other atom. So non-polar covalent bonds share the electrons equally between the 2 atoms. So this atom, so chlorine with its positive nucleus, positively charged nucleus, and this chlorine with its positively charged nucleus, because the electrons that they share are equally shared, both the charge across the whole molecule is 0. Charge on all the atoms is 0 because the electrons are equally shared. However, when the shared electrons are not equally shared between the 2 atoms, there's partial charges on the atoms. So think of this way. We know that hydrogen has a positively charged nucleus. We know that chlorine has a positively charged nucleus. But chlorine when it shares electrons with hydrogen, it pulls much harder on those electrons over to its side. So even the electron that hydrogen had before that is now shared more with chlorine than it was with hydrogen. The result is that the nucleus in hydrogen is left exposed. And remember that the nucleus has a positive charge. That when hydrogen is bound to a chlorine, its nucleus is left exposed without a balancing charge, negative charge. So the result is that it has a partial positive charge. And chlorine, because it keeps the electrons more over on its side, has more of a negative charge. So nonpolar, equally shared. Polar covalent, we have a partial positive charge and a partial negative charge. Ionic bonds, there's a complete transfer. So we have full charges, a full charge on sodium, full positive charge on sodium, full negative charge on chlorine. Small atoms usually with 6 or 7 valence electrons are electron hungry. So these are more electronegative atoms. They hold on, once they start sharing electrons, they hold on to those electrons more than the other atom does that they're bonded with. These atoms are what we call electronegative. So if hydrogen right here, and as, let me finish this. As we move across the periodic table from left to right, electronegativity increases. As we move from bottom to top, electronegativity increases. So the result is that fluorine right here is the most electronegative atom we have. Chlorine is a very electronegative atom. Oxygen is a very electronegative atom. When these three bind with hydrogen, creates a very non-polar covalent bond because they're so much more electronegative than hydrogen is. Atoms like hydrogen with 1 or 2 valence shell electrons have a very low electron attracting ability and are described as being electropositive. They tend to lose their valence electrons to more electronegative elements. Remember, hydrogen only has 1 valence electron. The electronegativity of an atom, its level of electronegativity or the degree of electronegativity depends on its atomic number. So the number of protons that it has. Because the more positive charge it has, the more likely it's going to grab more electrons that are negatively charged. The second thing that affects electronegativity is how far away are the valence electrons from the positively charged nucleus. The closer the valence electrons are to the atom's nucleus, the more electronegative that atom is. So the closer the valence shell electrons are, the more electronegative. And the more electronegative an atom is, the higher the ionization energy. This is the energy required to remove the most loosely bound electron. Remember that the farther the electron gets out, away from the nucleus, the easier it is to remove that electron. And the easier it is to remove an electron from an atom, the less electronegative that atom is. So atoms over here have a very high ionization energy. It takes a lot more to remove an electron from an electronegative atom. They hold their valence electrons a lot closer, and it's harder to remove the electrons for that reason. Have about 6 more minutes, so just hang on with me here. Water as a result of this electronegativity stuff going on, in water, H2O, the oxygen attracts the hydrogen electrons more strongly because it has greater electronegativity than hydrogen does. The result is that there's a partial positive charge on the hydrogen atoms and a partial negative charge on the oxygen. So non-polar molecules involve covalent bonds where the electrons are equally shared. Polar molecules involve covalent bonds where the electrons are unequally shared. So a polar covalent bond is formed when the electronegativity of the two atoms are very different. One of them is much more electronegative than the other. Like hydrogen and oxygen bound to oxygen, fluorine, or chloride, or bromine. So when we have polar covalent bonds within a molecule, there's this partial separation of charge where one side of the molecule has a partial positive charge, one side has a partial negative charge. The result is that a dipole is formed. There's a separation of charge. Polar molecules will orient themselves toward other dipoles. So the partial negative charge of one molecule is attracted to the partial positive charge of another molecule. And the partial negative charge of one molecule is repelled by the partial negative charge of the other molecule. So sodium, like right here, it's a sodium ion. When we dissolve sodium chloride in water, it ionizes, becomes an electrolyte. Ions or electrolytes in water have a very strong positive charge. Water with its electronegative oxygen and its electropositive hydrogens results in the oxygen having a high electronegative charge. And the hydrogens have a high partial positive charge. The result is that the water will organize itself so that the partial negative charges of the oxygen are the ones in interaction with the positive ion. And the partial positive charges of the water are farther away because they're repelled by this same charge. So they're oriented. And one more, and then I'll let you go. I know it's 1:44, so one more. So polar molecules play essential roles in chemical reactions. This ability to orient themselves with regards to other molecules. Are there any questions? All right, I will see you later. I'll see you on Thursday.
All
Thank you.
right.
Thank
Thanks.
you.
Thank you.
Bye.
Bye. Alexia, are you still there?